All right, our next speaker of the session is going to be Jesús Hernández Hernández, talking about rigidity phenomena of mapping class groups. Over to you.
Well, thank you very much. First of all, thank you to the organizers for allowing me to give this talk. Now, what I'm going to be talking about is, like the title says, rigidity phenomena on mapping class groups. Now, this can mean a lot of things, so I'm going to start from very, very low and start building up from there. And of course, there we go. So just to fix notation and give a fixed context for the results we're going to be talking about, let S be a connected orientable surface of finite topological type, you know, genus G and punctures. We are going to consider for this part that S has no boundary. And we're going to say that the complexity of the surface, which is just pretty much this number, is going to be greater or equal to 4, so that I don't need to consider special cases or low complexity cases, blah, blah, blah. Now that we have the surface, we are going to denote the extended mapping class group as this. And it's going to be just the group of isotopy classes of all self-homeomorphisms of S. And well, there's a place where this group acts very nicely, and that is the curve graph, which is just what you consider a curve in this talk as just a non-oriented topological embedding of the unit circle into the surface. And this curve is going to be essential if it is not isotopic to a point nor to a puncture. And the curve graph is just going to be the simplicial graph whose vertices are the isotopic classes of essential curves. And you're going to have edges if the corresponding vertices are have disjoint representatives. So things can be very nice, very easy. So for example, I don't know, if we take something like this is our surface. If I take this curve and this curve, let's say this is alpha, this is beta. In the curve graph, they're going to look something like this. Okay, so it's nice and easy. And we have a very natural action of the extended mapping class group on the curve graph. And just this. We can see it's well defined, and it's one of the first things that we start studying when we start studying the mapping class group. So given this action, you can have also this representation, naturally. And the first thing that you can ask is, what is true here? What does this action and this representation satisfy? It doesn't take long to see that this action in this context is going to be faithful, and it's going to be a co-bounded action. So, and it's going to be also not only by graph automorphisms, but it's also going to be by isometries. So there's a lot of work in geometric group theory, and particularly in the mapping class group subset of geometric group theory, that can be obtained using studying this action as an isometric action. But I don't know about you, but when I see a homomorphism such as this, there are several things that I wonder, and one of them is it surjective? Is it injective? Well, faithfulness gives us injectivity, so is it surjective? And if not, how does the image look like? And it turns out that we can formalize this a bit more. So in this talk, we're going to say that if we have a group G and an object X on which we are acting by automorphisms, the action is going to be rigid if the corresponding representation is going to be surjective. That is, every automorphism of our object is induced by an element of G. In this context, it would be if I take an automorphism of the curve graph, is it induced by a homeomorphism, by a mapping class? And Ivanov, Korkmaz, and Luo, in a very classical result of 97, if I'm not wrong, they told us that the action is actually rigid. Ivanov proved it for genus at least 2, and Korkmaz and Luo independently proved it for the remaining cases. So what we have here is that every automorphism is induced by a mapping class. Now we have that as a thing, we have as a result on one hand, and on the other, we have another action, a very natural action of the mapping class group, which is the action of conjugations by itself, by conjugations on itself. So we can ask the same question. If we have this action, does every automorphism of the mapping class group to itself comes from a conjugation? And it was a result by Ivanov that it is indeed the case. So in particular, the outer automorphism group of the extended mapping class group is going to be trivial. So now we have these two results, these two rigidity results of the actions. And at least a natural question for me would be how far we can push these results. How far can we generalize them and see if things work out? And that gives me, well, thinking of the fact that the outer automorphism group of the extended mapping class group is trivial, this gives me the following question that was first proved by Ivanov and then independently by Korkmaz and Luo, and say, okay, so we know that any automorphism from the extended mapping class group to itself is going to be a conjugation. So let's generalize it by taking subgroups. So, and not just any subgroup, let's start with finite index subgroups. So I start with gamma 1 and gamma 2 finite index subgroups, and an isomorphism from gamma 1 to gamma 2. It turns out that there exists a mapping class such that this isomorphism is just the restriction to gamma 1 of the conjugation. The way to obtain this result, at least the way Ivanov obtained it, is just paralleling one of the ways that most of rigidity can be proved. Why is this the case? Why does this matter? Is that, well, there is a relatively well-known analogy between certain semi-simple Lie groups with various adjectives and mapping class groups. Following this analogy, lattices in these Lie groups correspond to finite index subgroups, and the curve graph correspond to Tits buildings. And it's a well-known result that the automorphisms of the Tits buildings correspond to automorphisms of the groups. So in this case, it's just a matter of, okay, I take rigidity's proof via Tits buildings, and I just bring it over, sort of like translate it into the mapping class group setting. Things have to be proved, but they are not that hard. And by that, I mean that Ivanov did it in less than a page. So we have that. And moreover, the way that Ivanov proved this result is sort of algorithmic. It's kind of like a recipe. So in this recipe, you have the ingredient of certain generalizations of the result of the automorphism group of the curve graph. And by doing the steps in the recipe, what you obtain is this kind of results of algebraic rigidity. Now, that's actually how he proved this. He wanted to prove this result. He found the recipe, and so he said, okay, so I actually need to prove that any automorphism of the curve graph comes from a homeomorphism. He proved that. Now, like I said, since this gives us a recipe, a lot of results from that point onwards have been done trying to prove generalizations of the algebraic rigidity and thus obtaining combinatorial results. For example, Irmak and afterwards Verstock and Margalit for the remaining cases prove that if I have a map from the curve graph to itself that is a superinjective map, whatever that means right now, it's technically a generalization of an automorphism, then this map is actually going to be an automorphism. Now, following the recipe, this implies that we have the following. I sort of get rid of one of the finite index subgroups, and I just take gamma, finite index subgroup, and an injective homomorphism from the subgroup to the whole mapping class group, to the whole extended mapping class group. And it turns out that this is actually also going to be the restriction of a conjugation. So again, a combinatorial rigidity result gives us an algebraic rigidity result. Then, for example, Shackleton proved that if I have a local injective map, then this map is actually going to be an automorphism. So you also get an algebraic rigidity result. This one is a bit more technical, so it's not as easy to say in very few words, but it can be done. In general, it's just okay. You start with finite index, and you take a homomorphism that might not, a priori, might not be injective, but it's injective on certain restrictions. And it turns out that posteriori, it actually is going to be the restriction of an automorphism. So it's actually going to be injective and blah, blah, blah. Now, another result, this one is mine and independently by Irmak, is that you can just take any graph morphism from the core graph to itself, and this is going to be an automorphism. It doesn't matter, you don't need to add any other condition beyond that. It's going to be a graph morphism. And this actually is going to give you another algebraic rigidity result, but it's going to be a bit, the one that it gives you, it's a bit too technical, and it has too many conditions. It's going to be a generalization of the previous results, but it's not nice to see in a slide, so I'm going to omit it. Now, this is on the mapping class group setting. Now that we have this, we can start wondering, okay, how else can I generalize these results? There are several ways, there are many ways. You can start saying, okay, what happens if I change the surface to non-orientable surfaces? What happens if I take, instead of a finite type surface, what happens if I take an infinite type surface? What happens if I change from the core graph to some other simplicial graph associated to a surface? But all of this is still in the universe of the mapping class group. However, all of these results can also be asked for other families of groups. And the one I want to point out in this talk is about Artin-Tits groups. So how are we going to pass from extended mapping class groups to Artin-Tits groups? Well, what we're going to be doing that Ignat actually talked about in, I don't know, a few hours ago, I don't remember how long. Anyway, is that we are going to pass through the braid groups. So to do that, I'm going to be giving you a bit of history, not history, anyway, preliminaries, let's call it that. So take the closed unit disk and remove n points from its interior. And you are going to get the n-punctured disk. And define homeoplus as the group of orientation preserving self-homeomorphisms that, when restricted to the boundary, are the identity. That is important. And then define the mapping class group, classical mapping class group, if you want to add some adjective to it, as the isotopic classes relative to the boundary of this group. As it turns out, this is not necessarily a subgroup of the extended mapping class group, but anyway. So you have this. It turns out that you can actually give a presentation, a very nice presentation of who this guy is. And that is that it's actually the braid group in n strands. Now, for those of you that might remember or not, the braid group in n strands can be defined using the following presentation, just this one. I should have, sorry, for the Spanish, this should be something like if and otherwise. Sorry. Anyway, so this gives us an action of Bn on the curve graph, simply by saying, okay, I pass from Bn to the mapping class group, and then I act on the curve graph. However, this, I don't know about you, but this presentation, this action gives me, I don't know, it feels uncomfortable to me because it's not really a direct action. I have to pass through the mapping class group to act on the curve graph. And the relation between the braid group and the curve graph is not as direct as I would like. So what can we do to fix this? Well, there are two options. One of them is just find some other space where you can act, where the braid group is going to act, and see what happens. This, for example, was done by Matthew Calves, and he proved with this that, for example, many Artin groups modulo their center are actually asymmetric hyperbolic. But that's a bit hard, and that's getting farther away from the curve graph. So another way, another option is to give an algebraic interpretation related to the braid group of the curve graph, and that's what we are going to be doing. So you might just take some non-empty integral proper subinterval of this, and we say that the standard parabolic subgroup associated to it is going to be precisely the one that is generated by all of these guys. And on the other hand, a subgroup is going to be parabolic if there exists a non-empty integral proper subinterval such that H is conjugated to Pi. Okay? And with these definitions, I can define the parabolic subgroup graph. The vertex set is going to be all parabolic subgroups, and the edges are going to be, okay, take two subgroups, they are going to span an edge if one of these two conditions are satisfied. One of them is, well, one subgroup is containing the other. That happens. Another option is that their intersection is actually going to be trivial and the groups are going to commute. And with this definition, I can actually have the following result that is due to Cumplido, Gebhardt, Gonzalez Meneses, and Weist. And that is that if n is greater or equal to 3, there is, well, we have the classical isomorphism between the mapping class group of the disk and the braid groups. And then I can find a psi-equivariant isomorphism between the curve graph and the parabolic subgroup graph. So we are actually giving an algebraic interpretation to the curve graph. Now, all of this, all what I've just said, can be done not only on the braid group, at least the definitions can be done not only on the braid group, but on certain generalization of the braid groups, and that is the Artin-Tits groups. Now, by the way, how does this work? Well, it's not hard to do. Just take the n, you define these curves gamma n in this way, and then you say, okay, psi is going to map the then twist along gamma I to sigma I. Then you can prove that this is an isomorphism. And for the psi-equivariant isomorphism between the curve graph and the parabolic subgroup graph is that, well, you take an interval, then you define this curve as just saying, okay, take all the curves that correspond to the integral and the interval, and then just take the essential boundary, the unique essential boundary. It turns out that, well, you can define this, and non-trivial, the result is that this can be extended psi-equivariant, and you are going to obtain an isomorphism. Like I said, I'm just saying this is too easy, but it's actually very non-trivial. Now, how do I generalize this? Well, you can have a Coxeter graph. We already saw this in a previous talk, so I'm just going to say this a bit fast. So you have a Coxeter graph. You can define these guys, And then you can define these words. And as it turns out, the Artin-Tits group related with respect to gamma is going to be the group with this presentation. So we can see that this is indeed a generalization of the braid groups, because if I take gamma to be just this graph, for example, from 1, 2, 3, n minus 1, then as it turns out, if this is gamma, then A of gamma is going to be exactly, anyway, A of gamma is going to be exactly the braid group in n strands. So this is actually a generalization. So I can pull the definitions of parabolic subgroups from the braid groups into the Artin-Tits groups and take what does it mean to have a standard parabolic subgroup? What does it mean to be irreducible? Which is just that you're taking connected subgraphs of gamma. And then I'm going to say I have a irreducible parabolic subgroup if it is conjugate to some irreducible standard parabolic subgroup. And with this, I can just pull exactly the same definition as in for the parabolic subgroup graph, as in the vertices are the irreducible parabolic subgroups and the edges are given those relations. So in certain cases, as we've seen for the braid groups, the action of the Artin-Tits groups on these graphs mimic the action of the mapping class group on the curve graph. So we can ask ourselves how far this analogy can be pushed. So we have several open questions, and some of them are this. Are these graphs always hyperbolic? Because in the case of the braid group, they are the curve graph. And what about uniform hyperbolicity for certain families of Artin-Tits groups? Another open question would be if the action of the Artin-Tits groups is rigid here, as in if every automorphism of the parabolic subgraph is obtained from a conjugation of the Artin-Tits group. And if it is, great. If it isn't, how far is it actually from being rigid? And finally, at least for the questions that I am most concerned with, is what can be said about the combinatorial rigidity of this object. As in, if I take some graph morphism of this thing, does it come from an automorphism, or are there non-trivial graph morphisms in here? And we are working on these questions in particular with Bruno Cisneros, Rita Jimenez, and Israel Morales. And I'm done. Thank you.
Thanks. Let's thank the speaker. Are there any questions? So what do you believe the answers to be for those last three questions? Do you have any guesses or?
The answers would be sort of like, well, my guess would be they are not always going to be hyperbolic, but they are going to be hyperbolic in the nicer cases, whatever that means. And for this one, the answer is no, because, for example, with the braid group and the parabolic subgroup is not. However, the image of the representation has finite index, so it's not very far from being rigid. And from this one, for this one, I'd like to say yes, because I like things to be rigid, but to be honest, it's a completely open question which I have. I would be happy with either answer, but I'd be happier if the answer would be we have some sort of combinatorial rigidity.
Any other questions? All right, let's thank Jesus again. We have just 4 minutes till the next one. Okay, I have made you co-host, Radhika, so you should be able to share when you're ready. Oh, I see you have two devices here. All right, your second device should also be co-host now. Good. I don't hear you, Radhika. No, still nothing. Although I think I heard your iPad beep when it shared. There may be sound on your iPad, I'm not sure.
Can you hear me?